The year commenced with a symbolic milestone. The groundbreaking ceremony in 1919 marked the inception of this architectural endeavor. The construction efforts primarily focused on the development of a new power plant building in Töging am Inn, designed to harmonize seamlessly with the existing historical structure. Key highlights of the inaugural year included the commencement of the Inn Canal's construction, a pivotal component responsible for diverting essential water from the Inn River at Jettenbach-Töging to facilitate electricity generation. This canal's completion in 1924 was a significant achievement, laying the groundwork for the subsequent stages of the project. Simultaneously, planning and groundwork were underway, laying the foundation for the ambitious renewal of the weir system and the aging power plant building, which had served its purpose for almost a century. The vision of Verbund was not merely to replace but to revitalize. This commitment was exemplified by the comprehensive refurbishment undertaken on the power plant and weir system until 2022. This phase encompassed a fundamental overhaul, ensuring the structures met modern standards of efficiency and sustainability while retaining their historical significance. Throughout the year, preparations were made, setting the stage for the groundbreaking rejuvenation of this vital energy hub. The site's significance was emphasized by the construction activities, which were not only a testament to technological advancement, but also a nod to the historical and cultural heritage ingrained in the region. As the year drew to a close, the foundations were laid, both literally and figuratively, for what would become a transformative venture in the realm of renewable energy. The initial steps taken in 2019 not only symbolized the commencement of construction, but also heralded a new chapter in the utilization of Bavaria's natural resources for clean and sustainable electricity generation. The year commenced with the project entering its crucial phase, marking substantial milestones and accomplishments. Notably, the construction efforts were focused on bringing key components of the power plant to fruition. The remarkable progress included the completion of the machine hall, a pivotal structure housing the intricate machinery required for power generation. The installation of a fixed hall crane within the machine hall underscored the integration of modern technology within the historical context, exemplifying the project's commitment to efficiency and innovation. As the months progressed, the construction activities intensified, emphasizing precision and detail in the installation of essential components. A significant achievement was the installation of the support shovel ring for Turbine 2, an integral part responsible for bearing and distributing pressure forces within the structure. This meticulous assembly was a testament to the skilled craftsmanship and engineering prowess dedicated to the project. Simultaneously, the roofing of the machine hall in Töging neared completion, signifying a significant milestone in the construction timeline. The installation of the roof not only symbolized progress, but also ensured the protection and functionality of the crucial machinery housed within. Another noteworthy advancement was the placement of transformers within the front of the machine hall, a critical step in the process of converting turbine-generated electricity for integration into the high-voltage grid. This installation highlighted the intricate and interconnected nature of the power generation process. Towards the latter part of the year, a historic moment unfolded as the remaining operational machinery, serving faithfully for nearly a century within the historical Kraftwerk Töging, was finally retired. This marked a pivotal shift toward the completion phase. allowing the commencement of necessary works for the dry down of the inlet area, a crucial step before finalizing the construction. The year began with an air of anticipation as the project approached its climactic phase. With the majority of structural elements in place, the focus shifted to the meticulous assembly and integration of key components critical to the power plant's functionality. One of the hallmark achievements of the year was the completion of machines 1 and 2. These turbines, meticulously crafted and assembled, symbolized the pinnacle of engineering precision. Their successful completion represented a significant step towards the finalization of the power plant's operations. Additionally, the intricate machinery within the machines was meticulously installed, including the rotor and stator, essential components that would enable the generation of hydroelectric power. The assembly process required exceptional attention to detail and expertise, with engineers and workers meticulously aligning and integrating each component to ensure optimal functionality and performance. This phase of construction was a testament to the fusion of technological advancement and craftsmanship. The completion of Machine 3 was another pivotal milestone. With the installation of its turbine, rotor, stator, and associated components, the power plant was nearing its operational readiness. The seamless integration of these components highlighted the dedication and precision exhibited by the construction team. As the year progressed, the final touches were applied to the power plant's infrastructure. The completion of the powerhouse, the installation of necessary control systems, and the testing of machinery marked the concluding phases of construction. Simultaneously, external infrastructure, including the completion of the dry down of the inlet area and the finalization of pressure pipelines, emphasized the comprehensive nature of the project. These essential elements were crucial to ensuring the efficient operation and optimal performance of the hydroelectric power plant. Finally, as the year drew to a close, a momentous event unfolded: the successful testing and commissioning of the completed power plant. The rigorous testing phase, ensuring all systems were functioning seamlessly and in sync, marked the final stage before the project's official completion. The year 2022 heralded the successful realization of the ambitious hydroelectric project at Kraftwerk Jettenbach-Töging. The collaborative efforts, dedication, and expertise invested in the construction culminated in the establishment of a modern, efficient, and sustainable power plant. Before the TBM begins its work, planning takes place. This involves surveying the terrain, analyzing geological conditions, and considering the specific requirements of the project. Engineers assess factors such as ground composition, expected obstacles, and the tunnel's intended purpose. The deployment of a TBM involves assembling this colossal machine at the starting point of the tunnel. The TBM's components, including the cutting head, shield, backup systems, and segment handling mechanisms, are assembled and thoroughly checked for functionality. Once ready, the TBM is launched into the ground, marking the commencement of the excavation process. As the TBM advances forward, the cutting head rotates, grinding away at the rock or soil in its path. This continuous excavation process creates the tunnel's diameter, while the TBM's mechanisms simultaneously remove excavated materials. Depending on the specific TBM design and the nature of the ground, the excavated materials are either conveyed away through pipelines or transported via conveyor belts for disposal. segments of the tunnel lining, known as vissoirs, play a critical role in reinforcing the newly excavated tunnel walls. At regular intervals, the TBM places these prefabricated segments to form the tunnel's structural lining. These vissoirs are custom designed and manufactured to meet stringent standards, ensuring the tunnel's stability and strength against external pressures. The TBM operator, often referred to as the pilot, guides the machine's movement through the terrain. Using sophisticated guidance systems and precise control mechanisms, the pilot ensures the TBM's alignment, correct excavation depth, and proper placement of tunnel segments. The precision involved in this process is remarkable, often operating with tolerances measured in millimeters. Tunnel excavation using TBMs encounters various challenges, including unexpected geological features, changes in ground composition, or human-made structures encountered underground. To navigate these obstacles, TBMs are equipped with adaptable features and the ability to modify their operations to suit different conditions. Additionally, skilled operators monitor and adjust the TBM's performance in real time to overcome these challenges. Regular maintenance is crucial for TBM efficiency and safety. This includes inspections, repairs, and component replacements to ensure the machine operates optimally throughout the excavation process. Safety measures within the TBM, especially in confined spaces, are paramount, requiring meticulous attention and adherence to strict protocols to safeguard the workers involved in maintenance and operation. Continual advancements in TBM technology are aimed at enhancing performance, efficiency, and safety. Innovations in monitoring tools, maintenance robotics, and materials used for tunnel segments continuously push the boundaries of what is achievable, enabling the industry to overcome limitations imposed by geological constraints or physical laws. The creation of a forced pipeline typically initiates with comprehensive planning and feasibility studies. Engineers meticulously assess the terrain, considering the geographical landscape, soil composition, and any potential environmental impacts. Factors such as pressure requirements, flow rates, and the type of fluid being transported profoundly influence the design and material selection. Steel emerges as a preferred material for constructing forced pipelines due to its exceptional strength, durability, and resilience against the high pressures and environmental factors. The pipeline's dimensions, thickness, and welding techniques are precisely calculated to ensure structural integrity and longevity, meeting stringent safety standards. The actual construction process commences with site preparation, involving excavation and groundwork to accommodate the pipeline's route. This phase demands precision, as the pipeline's alignment and gradient must be accurately set to maintain the fluid's flow under pressure, without compromising its efficiency or safety. Specialized equipment and skilled labor are integral components of the construction phase. Welders proficient in joining steel sections fuse the pipeline, ensuring a seamless and robust connection. Quality control measures, such as non-destructive testing, are implemented to verify weld integrity, guaranteeing the pipeline's reliability. Simultaneously, ancillary infrastructure is established, including support structures, access points, and safety features. Valves, pressure gauges, and control systems are strategically placed along the pipeline to regulate flow, monitor pressure, and ensure operational control. Throughout the construction process, stringent adherence to safety protocols and environmental regulations remains paramount. Measures to prevent soil erosion, protect local ecosystems, and mitigate any potential impact on surrounding areas are diligently implemented. Once construction nears completion, rigorous testing procedures ensue to validate the pipeline's integrity and operational functionality. Hydraulic pressure tests and comprehensive inspections are conducted to detect any potential weaknesses or defects that could compromise the pipeline's performance. Upon successful testing and commissioning, the forced pipeline becomes operational, fulfilling its designated purpose. Whether delivering water to a hydroelectric power plant like the Romanche Gavet facility or transporting fluids for industrial processes, these pipelines play a crucial role in sustaining various sectors, supporting economic activities, and meeting societal needs. Nestled amidst the scenic Romanche Valley, the construction of this hydroelectric power plant began with a deep understanding of the region's hydrology. Engineers studied the flow of the Romanche River, assessing its water volume gradient and seasonal variations to optimize power generation while preserving the ecosystem. The plant's design incorporates a network of dams, reservoirs, and penstocks, channeling water with precision to drive turbines and generate electricity. The reservoirs strategically store water, ensuring a steady supply for power generation, especially during peak demand periods. One of the key components is the penstock, a pipeline that directs water under immense pressure from the reservoirs to the turbines. These turbines, coupled with generators, transform the kinetic energy of water into clean, renewable electricity. The construction process involved precision engineering, with a strong emphasis on sustainability and environmental preservation. Careful measures were implemented to mitigate any ecological impact, preserving local biodiversity and respecting natural habitats. Skilled labor and advanced construction techniques were employed to create structures capable of withstanding immense hydraulic forces. Concrete, steel, and other specialized materials were used to build robust infrastructure that could endure the rigors of harnessing water power. Moreover, the integration of state-of-the-art technology, such as automated control systems and monitoring devices, ensures the plant operates efficiently while adhering to stringent safety standards. Since 2016, an ambitious project has been underway in the heart of Paris, marking the inception of the Grand Paris Express. In tandem with the meticulous groundwork at Champigny Plateau, an essential component of this cutting-edge machinery, the TBM, took shape thousands of miles away in Germany at Herineck's state-of-the-art manufacturing facility. Upon completion, the behemoth TBM was disassembled, its components primed for transportation to its designated launch point, the Champigny Plateau shaft. The logistics of moving such a colossal piece of machinery demanded precision and expertise, ensuring its safe arrival for the commencement of its groundbreaking work. As the TBM's arrival drew near, the construction of the Champigny Plateau shaft continued with unwavering dedication. The intricate framework required to accommodate the TBM's ingress into the depths of the earth took shape, a testament to engineering precision and meticulous planning. Once on site, the assembly process began in earnest. The shield, a critical protective component, alongside various intricate elements, was meticulously lowered into the depths of the shaft and fitted together. Every step was methodically executed, ensuring the seamless integration of the TBM within its subterranean domain. The culmination of these efforts was the lowering of the TBM's mighty cutting wheel into the shaft, signifying the impending commencement of its groundbreaking work. The construction site bustled with purpose, arranged for the extraction and evacuation of debris, a critical aspect of the TBM's excavation process. Amidst this orchestrated symphony of engineering marvels, the first segments of the tunnel took shape. 60 dedicated workers, masters of their craft, toiled diligently, their collective expertise contributing to the realization of this monumental infrastructure project.